Good afternoon. In the last class we had discussed about the stress and strain. Today we are continuing our topic with modulus of elasticity and Poisson's ratio. Hooke's law. Everyone know this law. In 1679, Robert Hooke studied the stress-strain relationship of different solid material, and he proposed a law which is known as Hooke's law. And the law states that within the elastic limit, the stress is directly proportional to the strain. In the last class we had seen the load extension curve, isn't it? That load extension curve is identical to that of a variation of a stress with strain. That means load extension curve is similar to a stress strain graph. There you had seen a portion up to which stress and strain are linear. So that is below a limit which is known as elastic limit. So up to the elastic limit we know that the stress is directly proportional to strain, and that is Hooke's law. So within the elastic limit, the stress is directly proportional to the strain. That means stress directly proportional to strain, and changing the proportionality, we will get a constant. So stress is equal to a constant into strain. That constant is known as modulus of elasticity. So modulus of elasticity is equal to stress divided by strain. So you can draw the graph here also, the load extension curve or the load extension graph, which is similar to that of a stress strain graph. So while explaining Hooke's law, you can draw the stress strain graph along with this law. And as there are three types of stresses and strains, there are three types of modulus or moduli of elasticity. So the first one is Young's modulus Y. So it is the ratio of longitudinal stress to the longitudinal strain within the elastic limit. So Young's modulus Y is defined as the Young's modulus of a material is defined as the ratio of longitudinal stress to the longitudinal strain within the elastic limit. So here we can consider a wire of length capital L and having area of cross section small a, and this wire is suspended at one end and it is loaded at the other end. So what happens when this wire is loaded? Its length got increased, and that length increases by small l. So how can we write Y? Y is longitudinal stress by longitudinal strain. Now what is stress? Stress is force by area. So here F by A divided by longitudinal strain is change in length by original length. So L by small l by capital L. So rearranging, we will get Y is equal to F into capital L divided by small a into small l. So that is expression for the Young's modulus of a material. Here if we had suspended a mass M at the lower end, its weight mg will be acting downwards. So that is the force exerted on the wire. So here we can substitute F is equal to mg, where m is the mass attached at the free end. So that is the first modulus of elasticity, Young's modulus. Now the second one is bulk modulus. It is the ratio of the normal stress to the volume strain within the elastic limit. where we consider a body of a volume capital V and surface area small a, and a force F is acting normal to the surface so that its volume changes by small v. So what will be normal stress? Normal stress is force by area. What will be volume strain? Volume strain is change in volume by original volume. Now you can calculate bulk modulus by your own. So bulk modulus is equal to normal stress by volume strain, or volume stress by volume strain. So F by A by V by V, that is F into capital V divided by small a into small v. That is the expression for bulk modulus. Here this normal stress is also known as pressure. Force by area is also known as pressure, isn't it? So F by A can also be substituted as capital P, that represents pressure. Now what is the relation between pressure and volume? What happens when pressure is increased? So when pressure is increased, there will be a decrease in volume. That means pressure is inversely proportional to volume. So an increase in pressure is always accompanied by a decrease in volume. So if the pressure is increased by dP, the change in volume will be dV, isn't it? So the change in pressure is dP, so that the corresponding change in volume will be dV, but with a negative sign, because when the pressure is increased, volume gets decreased. So the decrease is denoted with a minus. So dP, if the pressure is increased by dP, the volume change is minus dV. So we had also already said that force by area, that is pressure. So we can substitute it as dP. In the case of normal stress, it is appropriate to write force by area as dP. So what will be bulk modulus? We had derived bulk modulus as F into capital V by small a into small v, isn't it? Now F by A can be replaced with dP. So, and dV can be replaced with minus dV. So the expression will be bulk modulus K is equal to minus V into dP by dV. So that is another expression for bulk modulus, where K is equal to minus V into dP by dV. And the reciprocal of this bulk modulus is known as compressibility, that is 1 by K. So that's about the bulk modulus. Now, as the pressure and volume changes in a gas can occur under two conditions, that is isothermal condition as well as adiabatic condition. We can define two elasticities for gases. In the section of bulk modulus, we had seen that the pressure and volume are inversely proportional, and this pressure and volume changes can occur under two conditions, either at a constant temperature, which is known as isothermal condition, and the other condition is adiabatic condition. So we can define two elasticities for gases also. So that's our next topic, isothermal and adiabatic elasticity of gases. So in the case of isothermal elasticity, pressure and volume of a gas change under isothermal conditions. That means the temperature will remain constant when pressure and volume of a gas changes. Then the elasticity is known as isothermal elasticity. And we know that for an isothermal process, P into V is equal to a constant. So that is the equation representing an isothermal process. You can take the differential of that equation. So P into dV plus V into dP is equal to 0. From that you can write P is equal to minus V into dP by dV. So minus dP divided by taking the V to the denominator, that is equal to minus dP divided by dV by dV. That is stress by strain again, that is bulk modulus, represented by K suffix I. So we got P is equal to Ki. So the isothermal elasticity Ki of the gas is the initial pressure P itself. So what we had done? We had taken the pressure and volume changes at a particular condition. Here the condition is at a constant temperature. That means the process is an isothermal process. Now the pressure and volume changes occurs at this constant temperature, and we had written the expression for isothermal process, that is PV equal to constant. Taking differential, we got P is equal to minus V into dP by dV, that is bulk modulus. So since it is an isothermal elasticity, we denote that Ki as isothermal elasticity of a gas, and which we got it as the initial pressure itself. Now the next type of elasticity is adiabatic elasticity, where the pressure and volume changes occur at adiabatic condition. And according to adiabatic process, PV raised to gamma equal to a constant. Again you can take the differentials. So P into gamma, V raised to gamma minus 1 dV plus V raised to gamma dP is equal to 0. From that, on simplifying, you will get gamma P is equal to minus V into dP by dV again. So that is expression for K, and suffix is A, that represents adiabatic elasticity. So Ka is equal to gamma into P. In the previous slide we got Ki is equal to P. So here Ki is equal to P, here Ka is equal to gamma into P. So taking the ratio of Ka with Ki, what you will get? Ka by Ki is equal to gamma. Now what is gamma? Gamma is the ratio of specific heats of gas. So gamma is equal to Ka by Ki, that is the ratio of adiabatic elasticity to isothermal elasticity, which is known as the ratio of specific heats of gas. Now the rigidity modulus. Rigidity modulus is the ratio of tangential stress to the shearing strain within the elastic limit. Here we can see the picture in the next slide, where we can consider a body in the form of a cube of a side L, so that its lower face ABCD is fixed and a force F is acting on the upper face tangential to the face. Now a force of reaction F acts on the lower face in an opposite direction. You can see a direction of F to be opposite in the lower face. These two equal and opposite forces will constitute a couple, and due to this couple, the cube displaces to A, B, C, D, E dash, F dash, G dash and H dash. So we had applied a force F towards right and a force of reaction F towards left forms a couple which displaces the cube towards right side. And the rotation of this cube, or the movement of this cube by the couple, is prevented by an equal and opposite couple formed by internal forces. So that is written here. we had considered a cube of side L. Lower face is fixed, F acting tangential to upper face. A force of reaction F acts at the lower fixed face in the opposite direction. Two equal and opposite forces will constitute a couple, and which displaces the cube to a new position, and this movement is prevented by an equal and opposite couple formed by internal forces. So now you can write the shearing strain. We know that the shearing strain is represented by theta, which is equal to change in dimension by original dimension. So L small l divided by capital L, because small l is the displacement occurred when the tangential force is applied. So small l by capital L. Now what is tangential stress? Shearing stress, again force by area, that is force by, it's a cube of side L, so the area is L square, F by L square. So what will be rigidity modulus? Stress by strain. So F into capital L divided by small a into small l. So that is expression for rigidity modulus. So all these modulus are obtained by taking the ratio of stress to strain, corresponding stress to corresponding strain, isn't it? So you can derive the SI unit of all the modulus, that is Young's modulus Y, bulk modulus K and rigidity modulus N, as Newton per meter square. You can do it as a homework, that is finding out the unit of modulus of elasticity. So that's are the three different types of moduli of elasticity. Now the next topic is Poisson's ratio, denoted by sigma. What happens when a wire is stretched? What happens to its length? When a wire is stretched, its length got increased, and that increase in length will be in the direction of applied force, isn't it? Now what happens to the diameter of that wire? When the length gets increased, the diameter gets contracted in a direction opposite to the direction of the applied force, isn't it? You can do it in your home by just try to expand a wire. By taking a rubber band, just pull it. You can see its length increases in the direction of applied force, but what happens to the diameter? Its diameter got decreased in a direction of the applied force. So there is a change in its length which is in the direction of applied force, and there is a change or contraction in its diameter or radius which is perpendicular to the applied force, isn't it? So two types of changes in its dimension occurs. So here we can define two types of strains. First one is lateral strain, that is defined as the ratio of change in dimension to original dimension perpendicular to the direction of applied force. That means the contraction represented by beta. And we already know what is longitudinal strain or linear strain, isn't it? It is the ratio of change in length by original length. Now the contraction is represented by lateral strain, which is the ratio of change in dimension to original dimension perpendicular to the direction of applied force beta. Now, how we can define Poisson's ratio? Poisson's ratio is defined as within the elastic limit, the lateral strain is proportional to longitudinal strain. So, beta represents the lateral strain and alpha represents the longitudinal strain. So, by law, within the elastic limit, the lateral strain is proportional to longitudinal strain, that is beta is proportional to alpha So beta will be a constant into alpha, and that constant is known as Poisson's ratio. So that sigma is given by beta by alpha. Now we are going to find out the expression for sigma in terms of beta and by replacing beta and alpha. So we can again consider a wire of length L, capital L, and diameter D. So what happens when a deforming force is applied? Its length increases by L and it decreases its diameter by small d. So longitudinal strain is linear strain, which is equal to alpha change in length by original length, that is L, small l by capital L. Now what is lateral strain? Beta, that is change in dimension, that is here the change in diameter by original diameter, small d by capital D. So Poisson's ratio sigma is equal to beta by alpha, that is L into small d divided by capital D into small l. This equation can also be written in differential form by substituting small l, that is the change in length, as dl and change in diameter as dd. So L into dd divided by d into dl. So that is a Poisson's ratio, and we know that Poisson's ratio is lateral strain by longitudinal strain. So both the denominator and numerator is of strain. So sigma, it will be a pure number with no unit as well as no dimension. So that's about the Poisson's ratio. Now we had already studied modulus of elasticity, different type of moduli of elasticity, and also Poisson's ratio. Now there is a relation connecting moduli of elasticity and sigma. So first one, the relation connecting y, k and sigma, that is k is equal to y divided by 3 into 1 minus 2 sigma. Relation connecting y and sigma, that is n is equal to y divided by 2 into 1 plus sigma. Then the relation connecting k and sigma, that is sigma is equal to 3k minus 2n by 6k plus 2n. The last relation which connects y, k and n, that means connecting the moduli of elasticity y, k and n, that is 9 by y is equal to 3 by n plus 1 by k. The first three relations connects the moduli of elasticity with Poisson's ratio, isn't it? And the last equation connects different types of moduli of elasticity. Now you had to study this, no need to study, or we don't have the derivation of these equations. Last time we have to study these four equations, and in the next slide we are going to find out the limiting values of Poisson's ratio, which all values are possible for Poisson's ratio. That is what meant by limiting values. For that we are taking the help of the first two equations of this slide. So our next topic, limiting values of Poisson's ratio. So we had the first equation, that is k is equal to y by 3 into 1 minus 2 sigma and n is equal to y divided by 2 into 1 plus sigma. From these two equations you can write the equation for y, isn't it? And you can equate that, so that the second equation, that is 3k into 1 minus 2 sigma is equal to 2n into 1 plus sigma. Think that sigma is positive. If a sigma is a positive value, what happens to the right hand side? 2n into 1 plus sigma will be positive. If a sigma is positive, 2n into 1 plus sigma will be positive. And this is equated with 3k into 1 minus 2 sigma, isn't it? So that term LHS must be always positive. So for LHS to be positive, 1 minus 2 sigma must be greater than 0. If 1 minus 2 sigma is greater than 0, 1 must be greater than 2 sigma, or 2 sigma must be less than 1, or sigma must be less than 1 by 2. That is the first case if sigma is positive. Now, what happens if sigma is negative? If a sigma is negative, the LHS of the above equation will be positive. If LHS is positive, RHS must be positive. For RHS to be positive, 1 plus sigma must be greater than 0. That means sigma must be greater than minus 1. So, the value of sigma lies between 1 by 2 and minus 1. 1 by 2 is 0.5, isn't it? So, theoretically, we can say that the limiting values of Poisson's ratio are minus 1 and 0.5. But experimental values are found to be in between 0.2 and 0.4. So here we can consider two different limiting values, either theoretical values that ranges from minus 1 to 0.5 or experimental values that ranges from 0.2 to 0.4. So that's about the limiting values of Poisson's ratio. Thank you.